Why high cell density occurs in VLSI designs and potential issues. High cell density refers to a situation where a large number of standard cells are placed within a limited area in a VLSI design. Here are some reasons why it can happen. Smaller feature sizes. As chip fabrication technologies advance, transistors and cells become smaller, allowing for more cells to be packed into the same area. This miniaturization is a key driver of Moore's law. Functional complexity. Modern VLSI circuits often perform complex functions, requiring a larger number of cells to implement the logic. Area constraints. The overall chip size might be limited by factors like cost or package constraints. This can lead to pressure to pack more cells into the available area, resulting in higher density. Potential issues with high cell density. Routing congestion. When too many cells are placed close together, there might be insufficient space for routing signals efficiently. This congestion can lead to longer routing paths, increased delays, and difficulty finding valid connections. Power dissipation. Higher cell density often translates to higher power consumption due to increased switching activity and leakage currents. Thermal concerns. Densely packed cells generate more heat, which can lead to thermal issues and potential reliability problems if not managed properly. Visualizing high cell density. Imagine a zoomed-in view of the chip core area. High cell density would appear as a large number of standard cells closely packed together, leaving minimal space between them. This contrasts with a lower density design where cells might be more spaced out with more room for routing channels. Mitigating high cell density issues. Placement optimization. Proper placement techniques like white space management and congestion-driven placement algorithms can help alleviate routing congestion. Power optimization techniques, clock gating, power gating, and low-power cell libraries can be used to reduce power consumption in dense designs. Thermal management. Techniques like heat sinks, floor planning for better heat dissipation, and power optimization all contribute to managing thermal concerns. Balancing density and performance. While achieving high cell density offers benefits like smaller chip size and potentially lower costs, it's crucial to find the right balance. VLSI designers strive to maximize cell density while managing routing congestion, power consumption, and thermal issues for optimal chip performance and reliability. I hope this explanation clarifies the reasons behind high cell density and its potential challenges in VLSI design. Factors affecting standard cell placement in VLSI. When placing standard cells in a VLSI design, there are several key factors to consider. 1. Timing optimization. Minimize net delays. The goal is to minimize the interconnect lengths between cells to reduce signal propagation delays. Shorter nets have lower delays, ensuring signals arrive at their destinations within the required timeframe. Tools often employ timing-driven placement algorithms to prioritize placement of cells on critical paths. 2. Power optimization. Reduce power consumption. Minimizing switching activity and leakage currents is crucial for low-power design. Tools might consider cell placement to optimize wire lengths and switching activity, potentially grouping cells with similar switching characteristics. 3. Routability. Facilitate routing. The placement should leave enough space for routing signals between cells efficiently. Tools might analyze potential routing congestion and adjust cell placement to minimize routing challenges. 4. Area utilization. Maximize core utilization. While minimizing routing space, the placement should also aim to efficiently utilize the available core area. This often involves balancing cell placement with potential white space and ensuring good packing density. 5. Design constraints. Respecting constraints. Specific placement constraints might be defined based on functionality or physical limitations. These could include placement of I/O cells near the chip boundary, keeping certain cells apart due to noise concerns, or aligning cells for efficient clock tree routing. Visualizing placement. Here's how you might visualize standard cell placement in a VLSI design. Imagine a rectangular area representing the core area of the chip. Standard cells are depicted as rectangular blocks with pins for connections. The placement tool arranges these cells within the core area, considering the factors mentioned above. Routing channels, spaces between cells, are then defined to allow for signal connections between the cells. Additional considerations. Cell placement tools. Specialized EDA tools are used to automate standard cell placement. These tools incorporate various algorithms and optimization techniques to achieve the best possible placement based on the specified design goals. Trade-offs. Balancing all these factors can involve trade-offs. For example, prioritizing timing might lead to slightly lower routability. Experienced designers use their knowledge to find an optimal balance for their specific design requirements. I hope this explanation clarifies the factors affecting standard cell placement in VLSI. Feel free to ask if you have any further questions.